Hi folks, this unit is looking at angular kinematics, angular dynamics, and kind of to start that we want to review rotations and talk about some things here. So really quickly, let's jump into that. So first, if you just remember with angular quantities, we talked about these back in the circular motion unit, but rotation angle we represent with theta. Angular velocity we represent with omega, and angular acceleration we represent with alpha. And these just work exactly like linear quantities. So angular rotation just tells you how much you've spun. Angular velocity tells you how quickly you're spinning. And angular acceleration tells you how quickly your speed that you're spinning with is changing. And just as a reminder, sorry, I put this down here. V equals R omega, X equals R theta, and A equals R alpha. If you wanted to convert these back convert between angular and linear quantities. So going forward, with angular vectors, we need to talk about something called the right-hand rule. And the idea behind this is for a vector, like for a spinning quantity, there's a vector associated with it. But like if it's constantly changing direction, how do we give that a direction? And so we use what we call the right-hand rule. So you take your right hand and you spin your fingers, and make sure you can see this, spin your fingers in the direction that the object, like this angle, is happening. So in this case, let me think, because I'm doing things mirrored. If it's this kind of rotation, then the direction of the vector points in the direction of my thumb. So let me draw an example for you. If you've got a disk like this, and it's spinning, around that way, then we take our right hand and we, have it copy the disk, right? You can see it's copying the disk, so our vector points up. So in this case, the angular velocity would be pointed upwards, we would say. Or this is the vector of angular velocity. So again, you're going to curl fingers in direction of rotation. And the thumb points in the direction of the vector. So again, I'll do an example of a disk rotating as shown below. What direction is omega? So I've got a disk down here, and I'm going to have it rotating, around like this, and then in the back rotating up. So again, we're going to do right-hand rule. So I'm looking at this picture, and I'm looking, my fingers need to go up. I think this might be, yeah, this is opposite for you. So it's going to look like this, and you'll see my thumb points what to you will be the right, because we're copying that rotation, right? Yeah, it comes down in the front and goes up in the back. So the angle points off to the right here. So that would be our omega. This is mostly an aside just because it'll come up later when we talk about angular momentum, but I want people to kind of be aware of how we talk about angles, angular quantities using vectors. All right, and then we have the four kinematics equations. So if you remember this back from in our previous units, we have these four equations. Delta V equals A bar delta T, delta X equals V naught delta T plus 1/2 a delta t squared, and then lastly v squared equals v naught squared plus 2a delta x. Now, if you remember, earlier I had said that we have these equations as well of x equals r omega, v equals r omega, sorry, x equals r theta, v equals r omega, a equals r alpha. And so basically, if we look at this, then when we come over here and if we substitute it in for all of these values, right, every single time, then we end up getting a bunch of extra r's that we can cancel out. And there's a couple places where it's a little weird, so it's not a perfect analogy, but basically all of these have direct analogs for angular quantities. So theta equals omega delta t, delta theta equals omega bar delta t, delta omega is equal to alpha bar delta t, delta theta is also equal to omega delta t plus 1/2 a, sorry, that should be an alpha delta t squared, and lastly omega squared is equal to omega naught squared plus 2 alpha delta theta. So in other words, all the kinematic stuff we learned also applies for angular quantities, just we have to use the angular kinematics values, so alpha, omega, and theta. So same idea, and this kind of intuitively makes sense, right? If I'm changing my angle at a certain rate, then after a certain amount of time, I'll have a certain amount of total angle change. Let's look at an example here. Large freight trains accelerate very slowly. Suppose one such train accelerates from rest, giving it a 0.35 meter radius wheels and angular accelerations of 0.250 radians per second squared. After the wheels have made 200 revolutions, assuming it doesn't slip, how far has the train moved down the tracks? What is the final angular velocity of the wheels and the linear velocity of the train? Well, 200 revolutions, nice thing here, this is really easy to calculate without any of this weird stuff. So A, 200 revolutions times 2 pi r will equal the distance, or the delta x, right? Because if the wheel kind of is unrolling, then we're just getting these circumference for each of these. So that gives us 400 pi times 0.350 meters, which gives us a distance of 440 meters, just looking at what I had written down earlier. This is just kind of a mathematical reasoning. There's no real physics involved here. But for part B, what is the final angular velocity? Well, we know that the r is equal to 0.35. We know that the alpha is equal to 0.250 radians per second squared. We know that the omega naught is equal to 0 radians per second. And we want to find the final velocity. And we also know this one's a little bit clever, but we can know that the change in theta is 200 times 2 pi, because one full rotation is 2 pi. So this is also equal to 400 pi radians. That's probably the trickiest one, is to know that delta theta. But now if we have a delta theta, we have an alpha, an omega, and we're looking for an omega final. Well, we want to use omega squared is equal to omega naught squared plus 2 alpha delta theta. And so in other words, omega is equal to, we know that initial omega is 0, square root of 2 alpha delta theta. And if you plug those values in, you'll end up finding that you get a speed of 25.1 radians per second. And then if we want to convert that to a velocity, well, we know v equals r omega. So v is equal to 0.350 meters times 25.1 radians per second, which will give us a speed of 8.77 meters per second. Remember again, a meters times a radian just gives you a different meters because it's converting between radius and arc length, because theta is equal to r theta is equal to s. So that's the idea behind this. It's the same sort of kinematic stuff, just instead of rotations, or instead of drawing along lines, we're dealing with rotations.